Welcome to today's lecture. So today we'll talk about random forests. The goal is as follows, or the lecture outline is as follows. We'll talk about a bit of motivation, and then we'll explain what random forests are, how to implement it with Python, and then we'll talk about some of the cool things you can do with random forests, such as extract feature importance and stuff like that. So what's the motivation? Before we even start talking, I guess, about random forests, let's go back to decision trees and just recall one of the main disadvantages of decision trees. So what I want you guys to do right now is just pause the video for a moment and try to recall or just think about what the major disadvantage or the drawbacks of decision trees were. Okay. So recall that decision trees suffer from high variance. So what this means is that if we were to split the training set randomly into 2 or 3 subsets and fit a decision tree on each subset, we could get fairly different results. So obviously this is an undesirable trait of a production machine learning model, right? So we want to build models that are robust. In other words, we want to build models that have low variance. What that means is that if we train our model on different subsets of the training set, we should consistently get very similar results. Otherwise, we cannot be sort of sure about the power of our model. So the goal is basically to kind of build a more robust model based on simple decision trees, okay? But a model that has significantly lower variance. Okay, so how does one build such a model? So the motivation comes from one of these, I guess, standard facts in statistics. So what I'm going to do right now is I'm just going to copy paste here some things that I wrote so that I don't have to type everything. So recall that if you have a sequence of n uncorrelated random variables, or very weakly correlated, and let's assume, for simplicity in this case, that they all have constant variance, okay? Then this is probably one of the first sort of standard things you show in statistics class, that the variance of the average of these the average basically, or the mean of these uncorrelated random variables is simply sigma squared over n. And the reason why this covariance sum goes away is because we assumed that these variables are uncorrelated. So in other words, what's happening here? So by summing up a bunch of uncorrelated random variables, we are decreasing the overall variance, okay? And this is precisely sort of where our motivation is going to be in terms of building these models, okay? Okay, so let's talk about random forests. So what are random forests? Okay, let me just write here real quick. All right, so random forests are a special example of what's known as ensemble models. So we'll discuss ensemble models in a little bit more detail later on, but what ensemble models really are is just a type of machine learning model that aggregates multiple lower level models into building a bigger, more robust and more complex model, basically. Okay, so random forest specifically, so these low learner or lower level models up in which random forests are built are exactly decision trees, okay? So in other words, random forests are built on the idea that fitting multiple decision trees and aggregating the results together is better. In other words, you should read that as you end up with a higher prediction and lower variance than fitting just a single tree. Okay, so let us just briefly describe how one fits random forests. or I mean the procedure for building a random forest. So again, what I'm going to do here, just so that I don't have to type everything from scratch again, I'm gonna just copy paste some of the my notes basically that I wrote earlier. Okay, and then we'll discuss them. Okay, so here is how random forests work. So you start with a given training set, okay, and then from that one training set you generate a certain number, let's say B, capital B, bootstrap samples. So what do we mean by bootstrap samples? All we mean by bootstrap samples is that we go into our training set B times and randomly sample subsets of a certain size, let's say K, okay, with a replacement, okay? So, and we do this because, you know, it's unfeasible. Like, I mean, in real life, you don't just have B training sets sitting there waiting for you, you know, to use. So that's why you use this powerful idea of bootstrapping, okay? Then, once you have selected these B, like randomly selected these B samples from your training set, you fit a decision tree on each of these B sub-training samples. I guess that's what we're going to call them. Now there is one thing here that we need to keep in mind. So, or an extra condition that goes with random forests. So basically, to obtain uncorrelated trees, because if we don't impose any restrictions, there is a danger that all the trees will be highly correlated, and that's why this formula here, or like we won't be able to kind of reduce the variance of the model significantly. So in order to obtain sort of highly uncorrelated trees, or like weakly correlated trees basically, what we typically do is that at each split, we kind of force the algorithm to pick only from a randomly selected subset of the features, of the total features that we have at our disposal, okay? And this way we avoid the following situation. So imagine that there is one feature in your subset that is extremely correlated, you know, very highly correlated with your outcome, and all of the other features are kind of equally correlated, like at a much lower level. Then when you fit these decision trees, say even if you fit 500 decision trees, the chances are that each of those, like the first node, like the first split, is going to happen at this one feature, and thus all the trees will be highly correlated, and it doesn't sort of matter how many of them you have, like you fit, the total variance is not going to be reduced significantly. Okay, so in other words, in each of these subsamples we fit a decision tree. So let's call this by f hat 1. This is basically the decision tree that you fit in the first subsample, and so on. Then for the regression setting, here is how you make predictions. So let's suppose that x naught is a new data point. Then you simply look at the average output of each of these B decision trees, right? So basically each of these decision trees, like Fi here, from where I goes from 1 to B, will give you a prediction for this new data point, right? So what you do is you sum all of those up and then you just divide by the number of the fitted trees. As we'll see, this procedure actually will significantly improve prediction power and again significantly decrease the variability of the model. In the classification setting, the way the prediction happens, so the simplest way is by majority vote. In other words, the predicted class for x naught is simply the most commonly occurring class among the B trees, right? Again, so each of the B trees will tell you, for example, in which class this new data point is. So all you do is you count all those outputs and then pick the one that came up the most. Okay. So we're going to try to keep this lecture kind of short and sweet, so to speak. So let's move right away to Python implementation and then just work on an exercise that's kind of interesting. Okay. So what I will do is I will use the for for now, I'll just use the insurance data set, but as an exercise, you'll also be required to use the airline satisfaction data set to build a random forest model. Okay, so for now, yeah, we're going to focus on random forest regressor, and then we'll go from there. Okay, so let's start by importing some of the standard libraries. NumPy as NP, import pandas as PD. So let's import some of the visualization libraries as we will actually need them. As PLT, import Seaborn. And, okay, what happened here? All right. And at the same time, let's go ahead and read in the data set. And is PD read CSV. All right, not test, I want to train. Okay, what happened there? All right, let's go. Good. So now let's just check the head of the data frame. It's a good practice just to see what you have. And so what we're going to do basically is, just like last time, I'm going to go ahead and drop every row that's missing a value, and I'm going to carry out these standard pre-processing steps basically. Okay. So let's go ahead and drop all the missing values. Let's just check real quick that we don't actually have any missing values. Actually, let me do this false as well. All right. Yeah, so we're good. We don't have any missing values. What I'm going to do again is break the features and the targets up, basically. So let's drop the charges. Okay, and then Y is going to be, and again, okay, what happened here? Axis, okay, cool. No. Dorp, okay, there we go. Drop, awesome. So again, it's a good practice to just check the head of your data frame and make sure that it is what it should be. So next thing I'm going to do is I'm just going to go ahead and turn these qualitative variables into quantitative ones. So this column, the sex column, the smoker column, and the region column. Get dummies, okay, so data is X, and then columns is calls, that's what we called it, and then I want to drop the first one. And I'm going to call this X again. So let's just check the head again. Cool. There we go. All right. So now we're actually in a position. So we have our data set is ready to be fitted. Okay. Fitting random forest regressor model. Okay. So let's go ahead and so for the time being, what we're going to do is we're also just going to split the data set into a training and a test set. Okay. So let's go ahead and import sklearn, import random forest regressor. And we're going to go ahead and import the train test split again as well. Okay, great. So let's go xtrain, xtest, ytrain, ytest. All right, so it's xy, and then training size, test size actually. Let's do test size. We're just going to set it at 30%. And we'll set a random state, I don't know, 42, it doesn't really matter at this point. Okay, so let's go ahead now and instantiate the random forest regressor. Okay, random forest regressor. And there's many parameters, just as with decision trees, most of those parameters are actually very similar to one another, except this n estimator. So this n estimator is basically, this is where you declare how many decision trees you want to fit. Okay. So for now, let's just decide to stay at 20. And then, so what criteria you want to use to fit the trees? It's set by default MSC, but let's just make it explicit. And we can use basically just as before the max depth. So let's just set a max depth of 3. And another feature which is kind of cool actually is what we talked about. So we want to build these 20 trees, but we want them to be as uncorrelated with one another as possible. So this is basically where we set a max feature. And we're going to set it 3. So typically you want to pick it, I think the standard choice is the roughly the square root of the total features that you have. So basically 3 or 4 is kind of what's recommended. But of course you should treat that as a hyperparameter when you tune your model. So this is what we're going to do a little bit later as well when we tune our model. Okay, so now that we've instantiated our random forest, let's fit it. And now the model is considered fitted. Okay. So let's start by making predictions. All right. And so RF pred, we're just going to use the predict method. And the predictions are done. So the next thing, so what's the next thing? So pause the video and think about what would you do next. Now that you have fitted the model, you've made predictions, what do you want to do next? Well, if you haven't figured it out yet, then what we're going to do next typically is assessing the power of your model or the performance of your model. So what we'll do first is we'll kind of gain a visual understanding of how good our model is. So what I mean by that, I'm just going to plot a simple scatter plot of the predicted values and the true values, like predicted charges and true charges. Okay, so PLT figure, fig size, let's do, I don't know, 8.6 maybe. And then, what did I call these? RF pred. Okay, so this is what it looks like. It does not look very good. So let's just make this, let's add x-axis and a y-axis so that we know what each means. So PLT x label, x label and y label. So this is true values. Let's make this 12, I guess, and then the y label is predicted values. Okay, great. Well, so visually we get kind of a sense of how well our model is doing, but maybe the majority of them are laying here, but there's a couple like this group that seems to be kind of falling off the line there. So what we're going to do is next is we're going to use some quantitative measures to get a feel for the performance of our model. Specifically, we're going to use the R2 score. Okay. So let's import it. All right, and then let's just compute it. All right, so we got about 78% of the R2 score. It does not look very good. Maybe we can do better. I mean, it's not too bad, but maybe we can do better. I think we should be able to do better. And part of the exercise at the end is going to be precisely to tune this model. But before we try to tune the model and measure the variability and like tune the parameters to sort of gain as much as we can out of the model, let's talk about another very cool thing that you can do with random forests. So random forests have a built-in attribute that makes it very easy to measure the relative importance of each of the features. So let me just show you that real quick. Let me do that. I guess I forgot to close that. Okay. So let me do that real quick, and then we'll turn to the exercise, and we'll actually compute, finish the first part of the exercise, and I'll leave it to you to finish the second part. So it's very easy. So once you've fitted the model, so then you can just recall, you can just call the feature coefficients from the RF reg, and I'll talk a little bit more what those numbers mean. Okay. So these are the coefficients. So let me create a nice data frame out of this so that we can read them better, and I'll explain what these numbers mean as well. So what I'm going to do is feed importance. So I'm going to create a data frame right here, and okay, so columns. This is going to be impurity. So maybe you can kind of guess what these numbers mean. Impurity reduced. And index is going to be X count. Okay, so let's see what this looks like. All right, so let me talk a little bit about what these numbers mean. So basically, what the algorithm does is it looks at how much the nodes that use a particular feature at a split reduce impurity. So this is done for each of the trees individually, and then the results are averaged across all the trees in the forest. Okay, so the higher the impurity reduced for a particular feature, the higher the relative importance of that particular feature with respect to the other features. Again, so let me just say that again. So basically what the algorithm does is for each tree, and for each split that happens, it looks at how much of the impurity was reduced when that split was made, and then you just average those over all the trees. Okay. Now here, since the feature smoker and then BMI and then age have the highest coefficients, like impurity coefficients here, what that means is that basically these are maybe the three features that the algorithm is relying the most when making predictions. If you recall, actually, when we fit decision trees, these three features were the ones that we saw I think when we looked at trees of depth 3. Like these were the only ones that were being used. Okay, great. So here is your exercise. Now we're basically done with the lecture, okay? So what I want you guys to do, if you haven't already done so, since I've posted these notes already on our course website. So what I want you guys to do is pause the video now and try to finish these exercises. Okay, so there's 2 tasks, but I mean you can go to town with these things and expand on them even more. So the first task is to gain an idea of the model variability as a function of the number of estimators, basically the function of the number as a function of the number of trees we're using, and the maximum depth, like how deep we're growing these trees. Okay, So that's exactly what we're going to do next. So we're going to build a tree. I mean, we're going to basically use cross-validation. So let me actually explain what the strategy is going to be. So the strategy is going to be as follows, and there's probably many ways to do this, but this is kind of what makes sense to me right now. So we're going to start by picking a maximum depth. We're going to sort of pre-specify a certain number of values that we want to, or depths that we want to look at, and for each max depth, for each max depth, we are going to use so for each tree depth, we will use cross-validation to fit a random forest with a different number of estimators, to obtain a sense of variability for different combinations of tree depth and number of estimators. Okay, so let's go ahead and import cross-validation. Cross-validate, and let's import kfold as well. All right, so again, as I said, we're going to have to specify a number of, and I think I use the default dictionary here as well. I'll explain it a little bit. So okay, so we're going to have to pre-specify a number of estimators. So, and P, let's see. Well, let's decide how many estimators we want to look at. So maybe we want to look, so when I say estimators, I actually mean like how many decision trees we want to fit. So let's start by fitting a tree so that we can compare the variability of fitting just a decision tree, and go maybe all the way to 50 and move each time, I don't know, like increase by 2. Okay. So maybe increase by 3 so that I don't have to fit too many trees. And then we'll have to have a number of depths that we want to look at. Okay, let's see. So NP, maybe I want to look at a depth of starting at 2 and then go all the way to, I don't know, 14 and move by 2. Or 15 and move by 2. Let's give it 14 and move by 2. Okay. Or actually, let me go for now just 11. So that I think it may take a while to run this. All right, so let's see, what do we want to do next? So let's instantiate a kfold. So n splits. We're going to start with 10 splits, shuffle, true, and random state. Let's do 101. Okay, so now, here's probably where things get a little bit complicated, since we have, so we need a way to store all of these results. So let me just say it again out loud what the strategy was. So for each depth that we pick here, I'm going to have to iterate over these estimators, or the number of trees, and for each number of tree I'm going to run cross-validation. So I'm going to have basically about, I don't know, like 15 or 16 different values here, or like cross-validation values. So I need a kind of a dictionary of dictionaries to store all of these guys in there. All right, so let me do that. So main results, maybe main results. This is gonna be a default dictionary, and I'm gonna have to pass a dictionary inside this dictionary. And here's why. It will become clear in just a little bit. So for let me just say this depths. I guess I'll make it plural so that I have it here. So for depth, in depths, Now remember, for each depth, okay, we're going to have to iterate over the estimators. And I want to keep track of that. So that's why I'm going to have another dictionary here. Okay, so what do I call this? Dictionary. Well, so let's be creative and call it depth dictionary. See what I did there? Okay. Now, what I'm going to do is we're going to have to create another for loop. So for estimator and estimators. And now we have to call cross-validation. Okay, so random forest, cross-validation. And then again, so now we've done this multiple times. So if you're confused about what's happening here, hopefully it will become clear in a little bit. But I mean, just pause the video and think about it a little bit. Okay, so here, random forest regressor. So number of estimators, again, is going to have to be a parameter. This is one of the estimators that we're looping over. Max depth, this is also a hyperparameter. We're looping over it as well. And let's see if I want to basically specify anything else. Maybe max feature. So I'm going to keep it at 3 for now. And then as part of the cross-validate, I'm gonna look at the R2 score, and I think this is basically it for now. Okay, so now here's what's happening. So once you pick a depth, then you're gonna have to loop over these estimators. So for each estimator, I'm gonna want to store that in this dictionary. Basically, I want to store the values, the R2 scores that come from the cross-validation for each estimator. Okay. So depth dict, and maybe, you know, so just to be so that it's clear what this means, so the key for each of these guys is gonna be n underscore est underscore, and then it's gonna be however many estimators I'm using at that stage. And then here is gonna be rf c cross validation test. Okay, R2. So this may actually take a little while, but okay. So now once I pick a depth and I loop over all these guys, right? So for that particular depth, I will have this dictionary that's associated with those depths, with that single depth, okay? So once I'm done with the second for loop, I have to store that whole dictionary in the main results there. Main results, and then for there, what do I want to call it? Okay, so I guess I'm going to call this depth underscore, and then I'm just going to call this by that name. And alright, so this has to be dictionary. This may actually, okay, what the heck is going on here? We forgot the training data. So outside here, training data, we forgot actually a couple of parameters, the training data, the cross-validation, and so on. Okay, so let's actually do it here. So x, y, cv is going to be af. Okay, hopefully this will not take too long, but it may actually take a few seconds. So here, I just want to show you guys what this object looks like. It's going to be a dictionary of dictionaries, basically. Okay, that didn't take too long. Okay, so here's what I mean, right? So for example, for depth 2, there's a dictionary associated with it where each key here is the number of estimators, and these guys are the R2 scores. Awesome. So what we're going to do next is we're just going to visualize this data set, okay, so that it actually looks nice. All right, so I have actually already done it, so not to waste too much time, I'm gonna go ahead and just copy paste that for you. Let me just look though, because I think I named some of the things here differently. So like this one, for example, main results. This one as well. Okay, this is actually not important, so I'm gonna actually just comment it out completely. So I guess the only thing that I renamed was, and I should have been smarter, I should have just gone here and renamed it there, but anyways, so I think we're almost done now. One more. And all I'm doing here, really, I'm just plotting these guys. So I'm just creating these box plots. Yeah, so you can have a look. If you have questions about this, we can definitely talk about it at some point. So how I built this graph. Okay, but let's, instead of focusing on how to build this graph, since we have basically done things like this before when we at the beginning of the course, when we talked about Matplotlib and Seaborn. So let's focus on what this graph actually tells us. So this one shows us, so this is where we used a tree depth of 2 with different number of estimators. So basically what I'm saying here is that we grew for all these different numbers of estimators, we always grew the tree only 2 levels deep, okay? So here, for example, we grew the tree 4 levels deep, 6 levels deep, 8 levels deep, and then 10 levels deep. So look at all of these guys. Well, virtually all, I guess. What do they have one thing in common? So one thing that kind of stands out is this first box that looks very long. Okay, it starts all the way here and goes all the way there. Very high variance. We saw that last time as well. So what that means is that if I use only one tree, if I fit only one tree, I get very different results, each time. So, and another thing that happens is that as you grow the number of estimators, or the number of trees that you're fitting, the results tend to kind of stabilize. But here we're growing the tree only to a depth of 2, so again we see some variance from a number of estimator to the next. And that's also something that you don't typically want to see in your model. You want kind of a steady state after a while. So for example, what's happening here, so if I keep growing the tree at a depth of 6 or the depth of 8, after a while, I mean, you're still going to see a little bit of variance because you're not fitting your data set on a single subset. But actually, there's not a whole lot of variance here. So remember, the 50% of your data is between, I don't know, 80 and 90%. And maybe if we fit more trees, or grew this guy a little bit deeper, or changed the number of features, you could even get tighter results. And that's actually exactly what you have to do in the second part of the exercise. So your goal there is to try to improve the overall results. But as you can see, like, you can kind of expect your model to have a performance, or like an R2 score around 85. That's kind of the mean. That's where the mean seems to kind of converge after a while. Okay, well, that's all I really had for this lecture. Next lecture, we're going to talk in more generality about ensemble models. We're going to focus on bagging classifiers, and we'll talk about like voting classifiers, and we'll discuss also a couple of boosting algorithms such as add a boost and stuff like that. So in the meantime, if you have questions, please send me an email and we can discuss them. Well, thank you for listening.